any problem of computer science is nothing but a mix of searching and sorting. So what I mean by that is, there might be a very complicated dynamic programming problem or graphs problem, but if you look at it closely, and if you understand, if you see what are the operations that you are performing, that is nothing but an intelligent variation of searching or sorting only. Okay, and searching, from here it looks like this is a very easy thing. I just have to search for something in a list or in an array. But if you look at it with a wide horizon, there are a lot of complicated problems that can be solved using searching alone. Okay, so first let's define what searching is. So let's say there is an array. I will take array as an example, as this is the simplest one. So let's say there is an array of size n. A problem of searching could be that search if an element k is present. Okay, so just check if an element k is present or not. If the element k is present, return me its index, and if it is not present, just return -1. Okay, so how many of you can write the code for this? How many of you can write the simple code that just checks whether an element is present or not and returns me the index? And if it is not present, I'll just return -1. Simple enough, right? So what I can do is I can just run a loop for I varying from 0 to n-1. If I see that array of I is equals to k, I'll return I. Okay. Else, if this loop is over, that means this element k was nowhere present. So I would simply return -1. Okay. This kind of code that you have written, sequential searching. So basically you started from one end, then you kept moving and moving and moving, and when you were done, you said that, hey, I don't have this value. This thing is called as linear search. Okay. Will there be weekly contest about the topics which were taught in that week? Yeah, we'll do that. Yeah. Okay, coming back to this. So this is called as linear search. Now guys, tell me one thing. What will be the time complexity of this code? What is the time complexity of this linear search algorithm in terms of n? Okay, so this is order n. But guys, don't you think that it actually depends upon what exactly are you searching? Because let's say my array contains 1, 2, 3, 4, 5, 9, 11. If I am searching for, let's say 1, I will get it here itself and I'll return it. So this is just order 1 operation. So don't you think it depends upon what I am searching for? The reality is it actually depends upon what I am searching for. But whenever you are to comment upon the time complexity, you comment about the worst case. Okay, and what will be the worst case here? What will be the worst case? Worst case will be when you are searching for, let's say, last element, or let's say when you are searching for something which is not present in this. If you are searching for, let's say, 7, which is not present in this. So basically, the time complexity of an algorithm that you talk about is always the time that it would take in the worst case scenario. Okay, is that clear? Cool. So yeah, so this is a very trivial linear search kind of thing that we can do. Now tell me one thing, can we search in a better way if my input space, or let's say I'll call it search space. If my search space is a little organized, okay, or let's say if it is sorted in some order, then can we do better? Can we do better searches if my search space is sorted? So the answer is yes, and most of you might have used it also. So tell me, how do you search for a word in dictionary? If you have to search for, let's say, wolf, do you start turning pages from A for apple, then B for ball? Do you do that? If you are searching for a word in dictionary, do you do that? No, you don't do that. What you do is you turn a random page, maybe middle page. If the middle page has a word that, let's say, starts with T, you know that W comes after, I think, T. So you move on to the right side. So entire idea is, if let's say my input is sorted, so let's say if I have A double P, B, C, D, E, K, L, and then let's say tiger, and then let's say this. Okay, let's say you are searching for this word and you stumbled upon this word. Okay, you know that these words are sorted on the basis of lexicographic manner. So if let's say the word that you are searching for is YZX, now if this is lexicographically smaller than this, you would say that everything towards the left is also lexicographically smaller. So you would move on towards the right side. Okay, so what is basically happening over here is, whenever I attack a middle element, okay, and this is sorted, my search space is sorted, I attack the middle element, I compare it with what I have to search. Now if this is smaller than what I have to search, then I can easily move on to the right hand side. And if this was let's say greater, if let's say this was greater, then everything towards the right would also be greater, so I would move on towards the left hand side. So you know, this kind of idea can be used to reduce the search space at a very high rate. In linear search, what you are doing, after one iteration, your search space is being reduced by 1 unit only. So if you are done with this, your search space is n minus 1. If you are done with this, search space is n minus 2. If you are done with this, search space is n minus 3. But in case of binary search, once you are done with something, your next search space is half of what it was. Now, if let's say you are searching from here to here and you stumbled upon here, you found that, let's say you are searching for something like 7, and if this is 17, and if this is sorted, you will search in this part. Now, this is the thing which is of interest to you. Now, let's say you stumbled upon something like here, which is 5. So you will say that, hey, everything towards the left is useless, I'll just check this. So every time your input size is being halved. So this would be much more optimized as compared to that. Is that clear how binary search is reducing my search space at a very high rate as compared to the linear search? Let's say I have an array which looks like 10, which is a sorted array, 10, 23, 40, 45, 56, 70, 93, 100, and let's say 121. Okay. See, to implement binary search, first most important thing is your search space, which is your search range, in which range you are going to search. Now that range can be defined here in terms of two variables, low, which is pointer to index of first element, and high, which is pointer to index of last element. So basically what I mean by that is that my search range is from index 0 to index 8, and whatever I am searching would exist from in between 0 to 8 only. Anything which is less than 0 is useless to me. Anything which is greater than 8 is also useless to me. Okay. And in this case, these range are inclusive range. By inclusive range, I mean to say that, let's say if this is the number line, then from x equals to 0 to x equals to 8 is the zone that is of interest to me. So guys, binary search can be implemented using inclusive ranges also, and it can be implemented using exclusive ranges also. So by exclusive range, I mean to say that you could have said that my answer, here in this case you are saying my answer would lie in between 0 to 8, inclusive. You would also have said that my answer would lie in between 0 to 9, exclusive. So this 9 is excluded, from 0 to 8 is where my answer lies. So I'm just saying this, you can go ahead with this kind of implementation also. We'll see that, but don't worry about that. Currently, let's focus our attention on the inclusive ranges. Is that clear what I'm trying to say? Exclusive, inclusive ranges. So currently we'll just focus on inclusive ranges, wherein I'm saying that my answer would lie in between low to high, where initially low is 0 and high is 8. So what do? Let's say I have to search for, let's say I am saying I want to search 100. I want to search 100. So first thing that I'll do is I'll find mid. And what will be mid? Mid will be low plus high by 2. So if you do 0 plus 8 by 2, you get index 4. Index 4 is 0, 1, 2, 3, 4. This value, 56. Is this greater than my search key or smaller than my search key? My search key is 100. Is this greater or smaller? So I can easily say that this 56 is actually what? Smaller than 100. Since this is smaller than 100, can I say that everything towards the left of this, including this, is useless for me? Can I say that now my attention can be focused just upon this part? Yes, no? Can I say that? And if I can say that, I basically want to move on to the next search space. Now, how do I move to the next search space? How do I move to the next search space? In order to move to the next search space, I have to change either low or high. What would you want to change? You would want to change low. So you can change your low to what? You can change your low to mid plus 1. So your mid was 4. Now your low becomes 4 plus 1, which is 5, which is pointing over here. Guys, one thing to understand over here is this low has to be strictly m plus 1. It cannot be m plus 2 or m plus 3 or something. Are you getting that? Because if you make it something like m plus 3, then you would just be venturing into this area, and it might so happen that your answer lies here. If you were finding 93, you would have missed out on that. Okay, so it has to be strictly mid plus 1, right? So yeah, so in this case you did your low equals to this. Now what will be your mid? It would be 5 plus 8 upon 2. This comes out to be how much? 13 by 2, which is 6. Okay, now 6 is this is 6. So what is this value? This 93 is still smaller than my search key. If this is smaller than my search key, what will I do? I'll again do low equals to mid plus 1. So now the value of my low becomes 7. Okay, so now low is 7, which is pointing over here. Now I'll do 7 plus 8 upon 2, which is 15 by 2, which is 7. Now this index, the value over here is exactly equal to what I was searching. So I can return this index as it is. Okay. So this was one quick dry run of the binary search algorithm, where you can see that first we had so much of input space, then we halved it, then again we halved it, and then eventually we found what we wanted to find. Okay. Can somebody tell me the time complexity of this approach, binary search? How much time is this going to take? Let's say I have an array of size n. How much time is this going to take? Okay, so there are different answers. So guys, look at it in this way. Initially, what is the size of my search space? What is the size of my search space in the beginning? If there are n elements, the size of my search space is n. Then what you do? You attack the middle element and you just compare it. You compare the middle element versus search key. Is this just an order 1 operation or not? Is this just an order 1 operation? That is exactly what you're doing. In every iteration, you just attack the middle element and compare it with the key. So you do some order 1 operation and then your search space is halved. So you reject everything either towards the left or towards the right. And the same thing that happened here would happen here also. That you would do order 1 operation and reduce it to n by 4. Same thing happens here, order 1 operation, reduce it to n by 8. How many levels will be there? From n to n by 2 to n by 4 to n by 8, there will be log n levels, and at each level order 1 work is done. So order 1 into log n is basically log n, and base would be 2. Okay, so this would be the time complexity. Is that clear? How is the time complexity of binary search log n by 2? Is that clear? Okay, cool. Now, tell me one thing. What would have happened if I was searching for something like 105? If in this, I was searching for something like 105, once more. So Joy, you want me to repeat the time complexity? You want me to repeat the time complexity? Just say yes if you, okay, cool. So do you understand that the initial search space was of size n, right? The initial search space was of size n. What did you do first? First, you attacked the middle element and checked if this is equal to the key that you are looking for or not. Okay. If this was equal to this key, you immediately return that, hey, I have found. And if this was, let's say, lesser than this, then you move on to the next half. Okay. So at each step, you are doing order one amount of work in comparing the middle element with the key. And then you are moving on to the halved space. And this is happening at each layer. So you are doing order one work, reducing your input space by half. Order one work, reducing your input space by half. It goes on and on. There are log n levels. At each level, just order one work is done. So this is order log n. Is that clear now? Does that make sense? Yes, no? Low would have project. Yeah, cool, cool, cool. So we'll see now that what is going to happen if I'm going to, let's say, search for something which is not present in the array. If there is something which is not present in the array, let's say I was searching for 105. My low was 7 and high was 8. Okay, low was 7 and high was 8. So do you understand this thing that low and high basically tells me the size of my search space. So low 7 and high 8 says that there are two elements currently in my search space. What does low 7 and high 7 mean? That means there is just one element in my search space. Now, when your search space becomes empty, that means you have nothing to search. You have searched everything and you did not get what you were looking for. And how that happens, when that happens, that we would inspect. Low is 7, high is 8. I am looking for 105. What will be mid? What will be mid when my low is 7 and high is 8? 7 plus 8 upon 2, that happens to be 7. So this 100, is this 100 smaller than this or greater? This is smaller than this. 100 is smaller than this. So if this is smaller than this, what do you do? If this is smaller than this, what do you change? Low or high? You change low. You change low. Your low becomes mid plus 1. Is it not? What do you change? Low or high? Somebody said mid equals to low plus 1. You don't change mid. You change your low or high depending upon your key value. See here, this value turns out to be smaller than what you are looking for. If this is smaller than what you are looking for, everything towards left is useless. So you would want to move right. Moving right means changing low to mid plus 1. So now your low would also become equal to 8. Right? Now when your low and high both are 8, what will be your mid here? Your mid again would be 8. Your mid again would be 8. And now 121, is it greater or smaller? Is it greater or smaller? This is greater. So if your mid is greater than what you are looking for, what do you change? You change your high. That is, you shift towards the left. So your high becomes mid minus 1. So now your high would become 7. The moment it happens that the value of high is smaller than the value of low, that means your search space is empty now. Did you get it? Yes, no, how many of you are following that? And the moment it happens, that means you can break out of the loop and you can easily say that, hey, I did not find the element and the game is over. Okay. So these were the critical things which you have to keep in mind while implementing binary search. You initialize low to the lowest answer that you can have, which is 0. You initialize high to the highest answer that you can have. Answer is index, okay? So what is the lowest possible index? 0. What is the highest possible index? N minus 1. And then you attack the middle element. You compare middle element with the key. If you find that middle element and key are exactly same, You return it as it is, otherwise you either move to right or you move to left. But the moment you see that high has become smaller than low, you just break out, because that means the search space is gone and now nothing is to be searched. Okay, cool. How many of you can implement it based on what I have just said? Just say yes, those of you who can implement it on your own. Okay, cool. So quick implementation. Low is initialized to 0. High is initialized to n minus 1. Now, while my low is lesser than equals to high, see, I have written this. Low lesser than equals to high means I still have something to search. There is still some space in which search can be made. Okay. Now find the middle, low plus high by 2. Compare the middle with the key. If you found it, return the index. Otherwise, two cases can be there. Either your middle element is smaller than k. If middle element is smaller than k, let's say this is 5, you are searching for 10. Since this is sorted, this is useless. You want to move here. So you would do low equals to mid plus 1. Else means that this was greater than what you were searching. So if let's say this was 15, that means everything towards the right would also be greater. So you want to shift to left. So you would do high equals to mid minus 1. Let this run. If you would have found something, you would have returned. And if you would not have found something, this loop would break. And then you can return minus 1 here. Coming back to what I had said initially, the bounds here are inclusive bounds. Okay. Low equals to 0 and high equals to n minus 1 are inclusive bounds. That means this also can be my answer. If let's say I am searching for 1 and 1 is present at index 0, this can be my answer. If I am searching for 5, 5 is present at index n minus 1, this n minus 1 can also be my answer. But you know, binary search, as I said, can also be implemented with exclusive bounds. And exclusive bounds, you understand, like if I write 0, 9, this signifies exclusion. That 9 is an impossible answer. Everything from 9 to infinity is impossible. Okay, and everything from 0 till 8 is possible. So we'll explore it out and you'll understand physical significance of this. Guys, in the meantime, answer me one question. Here, in this case, I was searching for an element called 105. Okay, I was searching for an element called 105. If let's say an element is not present, then which element would low and high eventually point to? I repeat, if I am searching for an element which is not present in the array, what would happen? Eventually my low would become greater than high and I would break, right? So what I am trying to say is, let's say you were searching for 105. Okay, here you were searching for 105. Now everyone just look here at the board. There was a point of time when my low was 7 and high was 8. And I was looking out for this. Now focus your attention here. What is your mid? Your mid is 7. This 100 is smaller than my key. If this is smaller than my key, I will do low equals to 7 plus 1. So low would become 8. Okay. Now when low becomes 8, my mid would be 8. 121, what is this? This is greater than what I am looking for. If this is greater than what I am looking for, what would I change? Low or high? What would I change? I would change my high and my high would become 7. And now since my high is smaller than my low, I would break. So what happens if the element is not present? Then low would point to the element in the array which is immediately greater than what I am searching for, and high would point to the element which is immediately smaller than what I am searching for. How many of you got what I said? Yes, no, did you get it? Okay, so this is a really, really important observation, and this comes in a lot handy. I'll explain it to you maybe through some other example, if some of you could not get it. So let's say my array is 10, 15, 22, 30, 40, 100. Okay. Let's say I'm searching for 25. Let's say I'm searching for 25. Can all of you do one exercise? To search for 25, what will be your initial value of low and initial value of high? What will be initial low? Tell me that. To start your binary search, your initial low would be 0. And what would be your high? 0, 1, 2, 3, 4, 5. 5. Can you all do a dry run and tell me what would be the final value of low and high when this loop breaks? What would be the final value of low and high when this loop breaks? Can you all do a quick dry run and tell me that? So first you get a mid. What is your first mid? From this low and this high, what is your first mid? 2. What is array of 2? Array of 2 is 22. If array of 2 is 22, then this 22 is greater than this or smaller than this. This is smaller than this. So what would you change? Low or high? What would you change in this case? You would change low. Can I say that now your low would become 3? Can I say that? Your low would become 3, right? Now when low is 3 and high is 5, what will be my mid? My mid would be 4. My mid is 4. What about this element? Is this element greater or smaller? This element is greater than this. So if this element is greater than this, what would you change? Low or high? High. What would your high be? Mid minus 1, which is 3. Okay. Now, this 30, is this 30 greater than 25 or smaller than 25? Greater or smaller? This 30 is greater than 25. If this is greater than 25, what would you change? Low or high? Low or high? You would change high. High becomes 2. The moment high becomes smaller than low, is this loop going to get broken? Is this loop going to get broken? Yeah. So what happens that the eventual element being pointed by low is something which is immediately greater than my key, and eventual element being pointed by high is something which is immediately smaller than my key. So if at all this element were to be present, this would be present between this and this. So basically, if an element is not present, eventual value of low and high would be pointing to the immediately greater and immediately smaller elements. Cool, cool. Now, one thing to understand over here is, let's say you are searching for an element which is greater than the greatest. Let's say you are searching for 105, which is greater than the greatest. What would low and high be eventually pointing to? What would low and high be eventually pointing to? If you are searching for an element that is greater than the greatest, if you run it, you will find that what does high point to? High point to something which is immediately smaller than this. So high would be here and low would have become n. Okay. And the opposite of this, if you were searching for something, let's say 5, which is smaller than the smallest. If you are looking for something which is smaller than the smallest, then what does high point to? High points to something which is immediately smaller than this. So it would be basically -1, okay, in terms of index, and your low would be index 1. Okay, so these would be few corner cases. Now let's say I have got an array of size n. This array is sorted. Okay, this array is sorted and the elements can be repeated. The elements can be repeated. Okay, sorted, but the elements can be repeated. So an example could be 1, 1, 2, 2, 2, 3, 4, and 4. Okay, now you are given a key. So you have to find first occurrence of that key. Okay, and if the key is not present, you have to return -1. Okay, so let's say my key is 4. What would you return? What would you return if my key is 4 in this case? What is the index of first occurrence of 4? What is this index? 0, 1, 2, 3, 4, 5, 6. I should return 6. Got it? So basically here elements can be repeated. Okay, elements can be repeated. But what I am saying that if I have given you a key, return me the index of first occurrence of that element if it is present. Okay, because if it is present, it can be present at multiple places. Like 2 is present at multiple places, but I'm just interested in the index of first occurrence, which is 0, 1, 2. And if it is not present, just return -1. Okay, so let us take a generic array. Okay, let's say this is my generic array. Okay, it has some elements. Okay, and let's say my key is 4. 4 is what I'm looking for, and since it is sorted, the same elements would be found in the same cluster. They would be clustered together adjacently. So 4, 4, 4, something like that you will have. Okay, so basically you start your binary search and you set your low equals to 0 and you set your high equals to n-1, and this is all your inclusive bound. You know that your answer can lie in between 0 to n-1 inclusive. Okay, now you attack middle element. Okay, that could be, let's say your first mid was this, let's say. Okay, if you find that a of mid is greater than key, if your a of mid is greater than key, what would you do? What would you do if your a of mid is greater than key? Since this array is sorted, and if my a of mid happens to be greater than 4, can I say that everything, let's say this was 7, can I say that everything including this towards the right of this is useless? Can I say that? Right? As simple as that. So I can simply do high equals to mid -1. Very good. Else if my a of mid was smaller than key, let's say I somehow stumbled upon here and let's say the value here was 2. In that case, can I say that everything towards the left of this including this is useless? Can I say that? In that case, what should I do? Should I simply do low equals to mid +1? Should I simply do this? Yes, no? Okay, cool. Now tell me one thing, what is the third case that remains? What is the third and final case that remains? When my a of mid becomes equal to key. Now, when my a of mid becomes equal to key. When my a of mid becomes equal to key, in that case, should I simply return mid? Should I simply return mid? No, we should not, because my a of mid could have become equal to key if even if my mid was here, or my mid was here, or my mid was here. But which value I am interested in? I am just interested in the first occurrence. I am just interested in the first occurrence. So I need a way to distinguish first occurrence from second, third, fourth, and other occurrences. Is it not? Is it not? I need a way to distinguish the first occurrence from the others. How can I do that? How do I distinguish first occurrence from others? Okay, so that should be simple enough. Let's say my mid is not at the first occurrence. Let's say my mid is not at the first occurrence. This is at, let's say, this occurrence. In that case, if you take a look at a of m-1, would it be exactly same as a of m? Would it be exactly same as a of m? Yeah. But if, let's say, my mid was at first occurrence, in that case, my A of m minus 1 would not be equal to this. It would be something that is smaller than this. Is it not? Is it not? Can you use this criteria to decide whether you are at answer or not? Okay. So here, when A of m, so basically this is corresponding to A of m equals to k. When A of m is equals to k, there are two cases. First case is something like this, where I actually am at the first occurrence. And second case could be something like this, where I am at non-first occurrence. Now I need a way to distinguish. So what I can do is that inside this else I can have an if condition, that if A of m minus 1 is not equals to A of m, then I can directly return m, that m is my first occurrence. Is that right? Is that right? Can I simply do that? That if A of m minus 1 is not equal to A of m, that means that m is the first occurrence of my key. But if this is not the case, then what should I do? If this is not the case, if let's say my mid was here, in that case, where would my answer lie? Where would the first occurrence lie? Can I definitely say it would lie towards the left? Can I say that? Yeah. So in that case, what should I do? I should simply do else high equals to mid minus 1. That's it. Is that clear? How many of you are clear with this? Just say yes, so if you are clear with this. Okay. Guys, look at this code and tell me, is there a corner case here? Can something go wrong here? I mean, logically this is correct, but can this code create a problem in runtime? Yeah. So actually this can create problem in runtime. So let's say this is the array and it contains 4, 4, 4, then 5, 5, and then some others. And let's say I am trying to find the first occurrence of 4. If I am trying to find the first occurrence of 4, eventually I would land at m equals to 0, right? While you keep shortening your search space, you would land at m equals to 0, is it not? You would land at m equals to 0. And when you land at m equals to 0, you would do this kind of check, because you see that A of m equals to search key. You would do A of 0 minus 1 is equals to this, and you will get an index out of bound exception here. Is it not? How many of you are getting that? That if the first occurrence of the key is at index 0, then this thing can create a trouble. So I need to fix it. So I can simply fix it by having an extra if condition, that if A of m is equals to key and m is equal to 0, that means that m equals to 0 itself is the first occurrence. I'll do low equals to 0, high equals to n minus 1. I'll say that while my low is lesser than equals to high, I'll find my middle element, which is low plus high by 2. Now I'll check if A of mid is greater than key. If A of mid is greater than key, what to do? Change my high. Else if A of mid is lesser than key. If A of mid is lesser than key, change my low. Else, now this is the main thing. If A of mid has become equal to key, which would happen here, then either I am at the first occurrence or I am at some second, third, fourth occurrence. Now, a special handling has to be done for m equals to 0. Okay. So if my m is equal to 0, return m, because that would be the first occurrence. Else if, now I am safe, because now I know that m is not 0. So this comparison can safely be made. Okay. So else if A of m minus 1 is not equals to key, that means that m is the first occurrence. Otherwise, if let's say I was at 4, which was my mid, and here also there is 4, there can be many other 4s towards this. So in that case, what should I change? High. and that should be mid minus 1, and eventually return minus 1. Is that clear? How many of you got the code? Just say yes if you got it. Yes, no. What would be the time complexity of this? Finding the first occurrence. Log n, right? Because in each iteration, whether you are in this if or this else if or this else if, you are just doing order one operation. You are just doing order one operation, and after each iteration, your search space is being reduced to half. Initially it was n, then n by 2, and so on. So this is just log n. Cool. So this was for finding the first occurrence. Can you find the last occurrence? I just compare the value of a of mid plus 1 with a of mid. So if a of mid plus 1 is something which is greater than a of mid, that means this mid is the last occurrence. Is it not? Can I say that? Can I say that? I can say that very easily. But if that is not the case, let's say I was here and I found that a of mid plus 1 is equal to a of mid. In that case, can I say there can be many other force towards the right? Can I say that? There can be many other force. So in this case, I should simply do low equals to mid plus 1. Is it not? Now, again, one thing here, that when you are at mid, you are comparing a of mid with a of mid plus 1. So again, do you see some kind of corner case coming in over here? Do you see some kind of corner case coming in over here? Yes. If the last occurrence of any element that you are looking for is at the last index, let's say this is the last index, then when you are here, then you might start comparing index n minus 1 with index n minus 1 plus 1, which is n, and you might get again index out of bound exception. So the case for mid equals to n minus 1 needs to be handled separately. Can you do that? Can you write the code yourself for this based on, it would exactly be the carbon copy of previous one with just few conditions in the last else block changed. Cool? Okay. Now you know how to find the first occurrence, you know how to find the last occurrence. Even this last occurrence has been found out in how much time? Had it just taken log n time? In just log n time, I have found out the last occurrence. Now let's say I want you to find the frequency of an element. Frequency of an element, frequency means how many times it is present in a sorted array. Can you find that in log n time? Can you find the frequency of an element in log n time? How can you find that? Using the exact concept that we have learned. So you can find the last occurrence, you can find the first occurrence. When you have last occurrence at index j and first occurrence at index I, that means this length, which is j minus I plus 1, would be the frequency of that element. Is that clear? That frequency of an element can be found out in a sorted array in log n time. This is a very frequently asked interview question. So guys, if you take a look at the implementation that we have done over here, there have been few if and else and some special cases that we had to handle. Like for last occurrence, we had to handle for the case when m was n minus 1, and for the first occurrence, we had to handle the case when m was equal to 0. Okay. Now you can solve this same problem without, you can write a different implementation where you don't have to worry about these things. So guys, this implementation is also fine. Its complexity is also log n. And what now I am going to tell you would also be log n. But now what I am going to tell you, you will have to listen very, very carefully, because this makes your code cleaner. This makes your code cleaner, and you can use this exact thing to solve tougher problems with much way cleaner code. Okay, so just take a look at that, everyone. Okay, let's first talk about the first occurrence that we were trying to find. Okay, cool. Tell me one thing, that let's say this is your array, and let's say this is the mid that you landed at. Okay. Now just tell me one thing, that if your a of mid is greater than or equal to key. Guys, be very careful about this. Greater than or equal to key. What I mean by that is this a of mid can be greater than the key also, can be equal to the key also, but I am not sure what exactly it is. I just know that this a of mid is greater than or equal to key. I don't exactly know whether this is greater or this is equal. In that case, what would you want to do? Think very carefully, then answer me. Would you want to do high equals to mid minus 1, or would you want to do something else? Okay, so I repeat. So let's say your key is 10. You are searching for 10. Okay. You landed at a value a of m, and your code found that this a of m is greater than equal to key. You just know that this is greater than or equal to key. You don't know whether this is exactly equal to the key or whether this is greater than the key. You don't know whether this is 10 or 11. This can be anything. In that case, would you want to, how would you want to change what? Would you want to do high equals to mid minus 1, or would you want to do high equals to mid? No. So Ashutosh, don't compare it also with anything. Just tell me, you just know this much of information, that a of mid is greater than or equal to key. What would you want to do? You would want to do high equals to mid minus 1, or you would want to do high equals to mid? So guys, in this case, let's say you do high equals to mid minus 1, there will be a problem. How many of you see that problem happening if I do high equals to mid minus 1? Because let's say if this element was 10 and this was the first occurrence and there were many other, okay, and I found that, hey, if this was greater than equals to this, then I did my high equals to mid minus 1. So basically my high comes here and low was somewhere back. So basically I missed out on the space that actually contains my answer. Is it not? What would be a wiser choice to make over here? If I just do high equals to mid, would it be a very safe and wise choice to make? Is it not? Would it be a safe and wiser choice to make? The answer is yes, because if, let's say, two cases could have been possible. If my key was exactly equal to a of mid, I can actually stop here, because anyways I am looking for first occurrence. So either this would be the first occurrence or something preceding this can be my first occurrence. Okay. And even if, let's say, this was something which was greater, still whatever my answer could be is towards the left of this, and I have not missed out on that. How many of you are following that, what I said? High equals to mid, just stopping there and there. Not doing high equals to mid minus 1, because I'm not sure whether that a of mid is actually the first occurrence or not. Are you getting what I'm trying to say? Anyone who wants me to repeat this? Okay. So you are at, let's say, mid. Okay. You are at mid and your key is 10. If you found that a of mid is greater than equal to key, two things could have happened. Either here you had 10, which actually was the first occurrence. Now, if you do high equals to mid minus 1, your high would come here and low is somewhere back. So now this is your search space and you missed out on the space that contained the answer. Okay, I'll explain that with search space. So let's say your low was something 0, and let's say your high was something 10. Okay, your mid came out to be 5. Okay, so this is index 5, this is index 6, this is index 7, this is index 4, and this is sorted array. So let's say here you had 10, and here you had 10, here you had 10. and here you had 9. Okay, you want to find the first occurrence of 10. If you find that a of m is greater than equal to key that I have written over here, in this case, if you do high equals to mid minus 1, what would happen? The value of high would become 4. And now you are in such a search space that is not containing the answer. So guys, the entire point that I am trying to make over here is that now this was about high, okay? So this was about the condition when a of mid was greater than equal to key. Now let's talk about other condition when a of mid is lesser than key. When a of mid is lesser than key, in that case, see, the entire idea is that my search space should never be such that I have lost track of my answer. Okay, so in this case, what I can do is whether I do low equals to mid plus 1 or whether I do low equals to mid, I will be in my answer zone. Whatever zone I would be in, that would be containing my answer, is it not? If a of mid is lesser than key, whether you do low equals to mid plus 1 or you do low equals to mid, you would be in your answer zone. Yes, sir, but we included comparing with a mid minus 1 in the code after finding it. Yeah, so currently just forget about that where you are comparing with a of mid minus 1. Now I'll just come to the point where this all thing will start making sense to you. So do you remember the, exclusive bound that I had talked about? Do you remember the exclusive bound where I say that my answer lies in between low to high, but this low is exclusive, something like that. Okay. So now here what I'm trying to say is I'll define my bounds in this way that my lower bound is exclusive and higher bound is inclusive. Okay. So now tell me what in terms of index, what is the highest possible index that you can think of? What is the highest possible index that can be your answer? What is the highest possible index that can be your answer if the array size is n? If the array size is n, the highest possible index that can be your answer would be n minus 1, right? N minus 1. And now I want this to be exclusive. So see, index 0 can be my answer. And there are many other lower indices, minus 1, minus 2, minus 3, so on till minus infinity, which cannot be my answer. These are impossible answers. So basically, I will choose minus 1 as my exclusive bound. So what I am saying is that my bound is from minus 1 to n minus 1. So basically, everything from minus 1 towards its left can never be my answer. And everything towards the right of this can also not be my answer, but from here till here can be my answer. Now what I am saying is, now be very, very sincere to what I am saying. Whenever you attack the middle element, so let's say this is your middle element. Whenever you attack your middle element and you find that this a of mid is greater than equal to key. If a of mid is greater than equal to key, what does that mean? Does that mean that your answer would now lie in between mid till here? Does that mean this? If your a of mid is greater than equal to key, can I simply do high equals to mid? And does that mean that now my range has got from here to here, from minus 1 to mid? Can I say that everything towards the right of mid until n minus 1 is now useless? Can I say that? That is the entire idea. So basically, this is the zone of possibility and this is the zone of impossibility and this is unexplored zone. Okay, this is unexplored zone. So now let's say this is your mid and you found that a of mid is lesser than key. If a of mid is lesser than key, you know that from this mid till here, answer is not going to lie. Is it not? From a of mid till here, answer is not going to lie. Can I say that if a of mid is lesser than key, if you are searching for let's say 10 and your mid is 5, that means from 5 till here, your answer is not going to lie. So you can quickly do low equals to this. So your low comes here And now this is here. This is your low and this is your high. Okay. So on, your zone keeps on shrinking on and on and on. Are you getting that, what I'm trying to do? So wherever my low is being positioned, that is saying from low towards its left, answer is not going to lie, including that low. And wherever my high is going to be positioned, that says from high, including this high, till low plus 1, my answer is going to lie. So eventually what will happen, that low will be some value x and high will be some value x plus 1. Okay. And now there is no unexplored zone in between them. Okay. So for sure I can say that this would be the first occurrence. X plus 1 would be the first occurrence. Whatever is the eventual value of high, if that is equal to the key, then that would be my first occurrence, if at all it exists. Did you get that? How many of you followed that? I would show it along with an example. If just say yes, those of you followed that, what I have tried to say over here. Okay, cool. So let us take a quick example to make things much easy. So look at this. Let's say this is my array and it contains 1, 3, 3, 3, 4, 4, 5, 5, 6, 6, and 7. Okay. Let's say I want to find the first occurrence of 3. Okay. Let's say I want to find the first occurrence of 3. I would initialize my low to -1 and I would initialize my high to 10. Okay. So you understand this -1 is exclusive and 10 is inclusive. Okay. What would be your mid? Do you see one thing over here, that everything including -1 and to its left is never going to be my answer, and everything from 10 till low plus 1 can be my answer. So what will be my mid over here? What will be the mid? Can you tell me the mid? Low plus high by 2, how much does that come out to be? 9 upon 2, that comes out to be 4. What is the value of array of 4? What is array of 4? 0, 1, 2, 3, 4. Array of 4. What is this? What is this? This is, can I say that here I have a of mid which is greater than equal to the key. A of mid is greater than equal to the key. So what should I do? What should I do? Should I change my high or should I change my low? Yes, I can do high equals to mid. So now my high is 4. Now you understand, this is basically saying that everything towards the right of this is useless for me. Okay, it's useless for me. And including this towards the left can be useful for me. Now what will be the mid? What will be the new mid now? Low plus high by 2, what will be the new mid? 4 minus 1 upon 2. How much does that come out to be? Does that come out to be 1? That comes out to be 1, right? Now this value is again greater than equal to 3, greater than equal to 3. So what should I do? What should I do? Should I change my low or high? Low or high? I should change my high. I should change my high. If my A of mid is greater than equal to, if my A of mid is greater than equal to key, I should change my high, right? Yes, no. Did you get that? Greater than equal to key, I should change my high. So now my high would be equal to 1. Let me write it here. This is low equals to -1. Okay. Now what will be the value of mid? What will be the value of mid? The value of mid now would be 0. And A of 0, 1. Is this smaller or is this greater? So this basically falls in this condition, that A of mid is lesser than K. Since A of mid is lesser than K, what should I do? What should I do? I should change my low or high. Low or high, I should change my low, and low would become equal to mid. So basically now low becomes equals to 0. So you're seeing that wherever low is positioned, if low is positioned at I, that means I and everything towards the left of I cannot be my answer. And wherever high is positioned, That means high and everything towards the right of high can be my answer. Okay, now since this is sorted and I am looking for the first occurrence, then this would be my answer. Whenever the difference between them is equal to 1, that means nothing is left in between, no space is left to be explored. So I can immediately say that high is going to be my answer. So basically you have to keep doing this process until high minus low is greater than 1. High minus low greater than 1 means what? That there is some space remaining that needs to be explored. And instead of doing high equals to mid minus 1 and low equals to mid plus 1, you are doing something other. Can somebody tell me why I started with low equals to minus 1? Can somebody tell me why I started with low equals to minus 1? For consistency of my definition is that I should be very, very sure that wherever my low is, everything towards the left of low, including this low, is impossible. Now, I can never do low equals to 0 because it might so happen that I am looking for the first occurrence of 1. If I am looking for the first occurrence of 1, this index 0 can be my answer. Okay? So, did you get it now? Out of all the impossible answers, whatever is the highest impossible answer, that you declare as your low, and then you go ahead. You can even do low equals to minus 2, low equals to minus infinity. That's up to you, but you will have to handle those cases when your index becomes negative, and then you'll have to switch accordingly. Did you get it now? How to change ranges and all. So, you know, if I have to write the code for this, the code for this would be, you know, extremely simple enough to be written. So I can do low equals to minus 1. I can do high equals to n minus 1. And I'll write while, what should be my termination condition? I just wrote it here. Can somebody repeat the termination condition for me? What should be my termination condition? Low lesser than high, or you can write like this, while high minus low greater than 1. Because high minus low, when high minus low becomes 1, that means low is x and high is x plus 1. No space is left to be explored. Okay, so in that case, if there is some space left to be explored, I do mid equals to low plus high by 2. And if my a of mid is greater than equals to k, what should I do? If a of mid is greater than equals to k, what should I do? Greater than equals to k, what is to be changed? High or low? High or low? And how is it to be changed? High. And high will be equal to mid. Else what should I do? Else what should I do? Low equals to mid. That's it. And when this code has finished execution, my high, if let's say when this code has finished its execution, two things could have happened. That let's say I am finding for a value that is present. So let's say I was finding for 3 and I am actually at the first occurrence of 3. Okay, high is here and low is maybe somewhere here, 2 or something. Then if I see that my array of high is equal to key, that means return this high. Now, if I was looking for a value that is not present, let's say I was looking for 3, which is not present. Okay, in that case, what could have happened? That I would not have arrived. If I was looking for 3, I would not have arrived at any 3. My high would have been here and my low would have been here. So in that case, I would have returned -1. So basically, if you take a look at it, eventual value of high would be at an index from where every element is greater than or equal to the key. And eventual value of low would be at an index from where every element is strictly smaller than the key. Got it? Got it? Yes, no, how many of you got it? Just say yes, low if you got it. Is low equals to mid plus 1 not more accurate? And not exactly, because you know the way I am defining low over here is low is my limit till where I am sure that this can never be my answer. But if you do low equals to mid plus 1, if let's say you found that the value at mid was 4, okay, which was smaller than the value that we're looking for, let's say 10. And if you do low equals to mid plus 1, then basically low becomes 5 now. And if here the first occurrence of 10 was there, you exclude it. You basically say that this is never going to be my answer. So you just have to position low at the place where you are sure that this is not going to be the answer. And you position your high at the place where you are sure that this can be the answer. Got it? Is that clear? How many of you are clear with this kind of implementation? A lot of people get confused with this kind of implementation, that how low and high is being changed in this way. If you understand the physical significance of low and high very, very clearly, you will be easily able to understand why this kind of changes are being made. Any doubts in this? Did you get it? Is this code way cleaner than the previous code that we had written using inclusive bounds and makes less comparisons also? And if you have to find the last occurrence, how would you initialize your low and high? How would you initialize your low and high? Okay. So guys, let's take a look over here. Let's say I want to find the last occurrence. Let's say I have 2, 2, 2. Okay. Tell me one thing. If you find that A of mid is lesser than or equal to key, if A of mid is lesser than or equal to key, can I say that my answer would lie in between mid till high? Can I say that? If A of mid is lesser than or equals to key, can I say this thing? That my answer would lie in between mid till high. So in this case, can I directly change my low to mid? Can I directly change my low to mid? Okay, so basically here the idea is that low is going to be my inclusive bound and high is going to be my exclusive bound. Because if I see that, let's say A of mid is greater than key. If A of mid is greater than key, can I say that everything from mid till infinity is impossible? So in this case, I can change high equals to m. Is that clear? Can I do that? Can I do that or not? Okay, so can you initialize low and high? How can I initialize low and high here? So can you tell me the lowest possible answer, lowest possible index that you can get? What would be the lowest possible index? Can I say that would be 0? Okay, and there can be many values of high which are impossible. Can you tell me some impossible values of high? What are the impossible values of high? So n, n plus 1, n plus 2, these all are impossible. So I can prefer to go for n. And now I can say that my answer lies in between 0 to n. Now I say that my answer lies in between 0 to n. I attack my mid. If A of mid is lesser than equals to key, if A of mid is lesser than equals to key, I change my low to mid. And if this is the case, I change my high to mid. Okay. And here eventually whatever element would be pointed by low, that would be the last occurrence of your key, if at all it is present. Is that clear? Did you get it also? Are you feeling comfortable now with exclusive bounds? I told you about exclusive bounds because it makes your code cleaner, and in some complicated problems, if you implement this way, it's quicker enough to implement. Got it? Anyone having any doubt in this? With exclusive bounds? How many of you can write code on your own of finding last occurrence and first occurrence using these exclusive bounds? No, the only thing that you have to be little wary about is choosing which bound is to be inclusive and which bound is to be exclusive. Okay, if you are clear about that, then things are simple. Okay, and even if you're not so clear today, you will become over the time. Okay, so cool.